diffraction. Are there any questions on those? Anything that's not clear? So if you can see the board here, basically what we're talking about is if you have crystallographic planes, each line here is a plane. We talked about the Miller indices of the planes. The planes could be 110, 100, 132, 213, any type of plane within the crystallographic lattice. You will have a series of equally spaced planes. So the spacing between the planes is what we call interplanar spacing, which is called a D. Now, the way we are doing this is we kind of send an X-ray and then get that diffracted, and then you have another X-ray coming and going around this one. So this is the ray number 1, this is ray number 2. Now, for a constructive interference to happen between ray 1 and ray 2, the path difference, as you can see very clearly, ray 2 is traveling an extra distance of let's say it's a P and P, 2P. That is the extra distance the ray number 2 is traveling. So that's what we call the path difference. That is the difference in the total distance the waves are traveling. As long as the path difference is an integral multiple of the lambda, which is the wavelength of the light, then the theory says there should be constructive interference. So by changing the angle, by knowing the angle here, the P then will be d sine theta, because that's your D here, that's the distance between the planes, and that is your diagonal there. So d sine theta plus 2 d sine theta is 2d sine theta, which is in lambda. In most of the problems, you can assume n equals to 1. That is the first order diffraction. Unless otherwise it is specified that you are dealing with a second order diffraction, you can assume that n equals 1 in most of the cases. All right, so typically the kind of problems they will do is find the 2 theta value when wavelength of 1.540518 angstroms of light is diffracting a plane with an interplanar spacing of 3.12 angstroms. So if I know the distance between the planes and if I know the wavelength, would I be able to find out the angle of the X-ray that has to hit that plane in order to have a constructive interference? Okay. So to do this calculation, you know already 2, D is 3.12 times sine theta equals n lambda. Again, I told you just a minute ago, n is 1 otherwise, unless otherwise specified. So we can just say simply it's 1.540518 angstroms. So with this, you can find the value of sine theta, which is 1.540518 divided by 2 times 3.12. Once you have this value, you can get the theta value, which is a sine inverse of the same thing here. Can anyone quickly calculate and tell me what the theta value is? Can you all see this board, right? So what is the theta value here? I want you to practice doing this. (1.540518) divided by 2 times 3.12, and get that number, take the sine inverse of it and tell me what that is. Anyone?
I guess 0.2397.
No.
Maybe.
Are you in degrees or radians?
Is it 14.3?
14.3 is correct. That's your theta value. Usually in X-ray diffraction language, they always talk about 2 theta. So 2 theta will be 28.6 degrees. this technique is so powerful that it is used to solve the structures of so many compounds like sodium chloride, calcium oxide, titanium dioxide. Even DNA structure was solved using this technique, X-ray diffraction. The DNA, RNA, most of the proteins, enzymes, these are all studied by X-ray diffraction to understand the arrangement of atoms. So if something is a solid and crystalline, then chances are that you can use this technique to resolve the atomic arrangement inside the solids. So Bill and Larry Bragg, who invented this technique, father and son team, got a Nobel Prize for this discovery. It's a very important technique. Even FBI uses this technique to figure out different solids that look white. You know, if you find somebody carrying a white powder, the suspicion it could be a chalk powder, it could be sugar powder, it could be a salt powder, or it could be a drug. Yeah, so the way they do this is just do an X-ray diffraction experiment and see what the pattern looks like. At what angles are you seeing constructive interference? The beauty of it is no two solids will have exactly identical diffraction pattern. It's almost like a fingerprint of a solid. So that's what the FBI will find out, you know, what that powder is within about 10 minutes time. Okay, so this is a very powerful tool, and we do have, unfortunately, because of the COVID, I'm not able to take you down and show you the powerful diffraction system that we have at Rowan University. But maybe post-pandemic, if some of you are interested, I can show you how to run the samples and how to identify them. All right. Any questions on the diffraction? I just showed you a sample problem. You have three unknowns, the d spacing, theta, and the lambda. Given two of them, you should be able to find the third one very easily. So you should practice doing these problems too. Any other questions? Anything that's not clear so far? Okay, so the next topic that we're going to work on is types of solids, usually. In terms of solids, there are something called polytypes. Two solids are called polytypes if they have exactly same arrangement in 2 dimensions, but differ in the 3rd dimension of the packing. That is when we say they are polytypes. So in the 2-dimensional, they look exactly same, but the 3rd dimension is different. So if 2 solids differ in the packing in the 3rd dimension, we call them polytypes. Similarly, we have another term called polymorphs. Polymorphs are for the same compound when the same compound can adapt more than one type of crystal structure. For example, when you look at carbon, carbon can be graphite or it could be a diamond. The structures of those two are very different. Graphite is a 2-dimensional anisotropic solid, a diamond is a 3-dimensional network. It's extremely hard. Similarly, tin has 2 crystallographic forms, the white tin and the gray tin. So below 14.2 degrees, we have white tin, but when you increase the temperature, you get into gray tin. So it's the temperature that changes the crystal structure in some cases. Like, for example, you have iron. Iron is a BCC structure up to 906 degrees. This is what they call the alpha iron. And when you heat it above 900 degrees Celsius, it changes to FCC. And between BCC and there is a hexagonal close packing too. And if you go to extremely very high temperatures, above 1400 degrees, it again comes back to BCC. So these are all the polymorphism of iron. At room temperature, it is BCC, body-centered cube. It's called alpha iron. And then you have the beta iron, and then you have the gamma iron, and then back to alpha. So these are all the variations that make the study of the solids extremely interesting. So the properties of iron change when you change the temperature, because the packing efficiencies, all that stuff is very different in these cases. So I hope you're getting a feeling of what polymorphs are, right? Any questions, you can always open your mic, and we'll be more than happy to give you more examples. So these are all the terms that we use in solid state chemistry. The next thing is, when you mix two solids, two metals, for example, we get what we call solid solutions. You have to keep in mind that gases are always soluble in each other. Liquids, some are miscible, some are immiscible. But in solids, the story is very different. In some cases, you get miscibility. In some cases, you don't have any miscibility. In some cases, what happens is you have a solubility up to 10%, and then there is a solubility gap, which implies that they, remember, it cannot be soluble. And then when you increase that amount by about 80%, again, they start becoming soluble. So there is always this complex story about the solid solutions. In solid solutions, we have two different types. One are called homogeneous. Like copper and zinc, for example, you can mix them in any ratio that you want. You can get homogeneous solid solution of the alloys. So these are homogeneous alloys. An alloy is basically a compound that is made from two or more metals. So it's good to keep that definition. You can also have solid solutions which are hetero. So these are two types. One we call intermetallics. What is an intermetallic? An intermetallic is a compound between two or more metals with fixed stoichiometry. Like, for example, if I have Cu3Zn, that is an intermetallic. So because I have copper and zinc in a particular ratio of 3:1. But if you have a continuous solid solution, then we call them alloys. So the difference between alloys and intermetallics is seen here. Intermetallics generally have fixed ratios. Similarly, when you're making homogeneous alloys, you can have two types. One is called substitutional, and the other one is called interstitial. So, for example, in a substitutional solid solution, let's say this is my host network of atoms arranged in this. And if you put a guest atom into this, and if the guest atom occupies one of the positions of the host lattice, then we call that substitutional solid solution. All right. On the other hand, sometimes when you add a guest atom to the host matrix, the guest atom might occupy a space in between, in which case we call that interstitial solid solution. So both types are possible. For example, if I have iron, and if you put a little bit of carbon, it forms an interstitial solid solution. Carburized iron, which is basically the stainless steel, right? I mean, you can put a little bit of carbon and improve the mechanical properties of the iron. That carbon occupies the interstitial space in the iron network. All right. On the other hand, if you have iron and cobalt, you can have substitutional solid solution. So what is the rationale? How do we know which one is substitutional, which one is interstitial? Usually, substitutional alloys are formed when the radius of the atoms is within 15% of each other. Okay. On the other hand, if the radius is more than 15% different from the host atom, then we can say it's an interstitial solid solution. So for example, if I have potassium, which is 1.43 angstroms, I'm just giving you an estimate here, and the other one is sodium, let's say it's 0.94 angstroms. So when you mix potassium and sodium, mix them, what type of solid solutions we get? Do we get interstitial or substitutional? So what's the difference here in the ratios here, the radius ratios? I can give you an answer, or you can perhaps work it out and tell me whether those radii are within 15% of each other, or is it above 15% of each other? What is 15% of 1.43? Can anyone quickly calculate? I don't have a calculator here with me.
It's 0.21.
Hmm?
0.21.
Is 15% of 1.43?
Yes.
Yeah.
Okay, so if you subtract 0.21 here, right? What do you get here? This is 2 to 1.22, right? So if the radius of the host guest atom is 1.22 or more, you're going to get substitutional. But sodium here in this case is much smaller. So this is not going to make substitutional solid solution. Instead, it makes interstitial solid solution. So if there is a problem of two metals, and if I give you the atoms and ask you what type of a solid solution would you expect, you should calculate the number and then see whether it is within 15% of each other or not. Am I clear here, folks? Any questions? Is everything okay?
Yes, why is it the radius? Why is it 15%?
That is because when you try to put an extremely large or a small atom here, right, the lattice distorts so much that it will not be stable in that position.
Got it.
So when you're replacing an atom with another atom, you have to make sure that they have similar sizes. If they're extremely different sizes, like for example, if you have grapes and if you want to put a pumpkin, right, that's going to distort the structure of the grapes, the size difference. And that strain is good enough for the compound to break down, so it won't form. That makes sense?
Yes, thank you.
Very good. Any questions, folks? Good. So the other type of alloys are very special compounds. I want you to go and look at your periodic table as you are listening to this lecture. I mean, most of inorganic chemistry you cannot learn unless you have a periodic table next to each other. There are special class of alloys that are made from extremely electropositive elements, which are basically on the left-hand side of the periodic table, like sodium, potassium, barium. These are all extremely what we call electropositive, calcium. On the other hand, you also have highly electronegative metals. So if you go on to the right-hand side of the periodic table, especially in the main group, you have lead, bismuth, right, thallium. These are, we call extremely electronegative metals. Both are metals. So when you try to make an alloy between an extremely electropositive metal like sodium and then mix it with thallium, for example, you make an alloy, and these alloys are called Zintel phases. Okay, these have extremely very different properties. For example, in the case of sodium thalide looks pretty similar to diamond, although it's not carbon, but when you make it, the appearance-wise, right? The reason for that is sodium loses an electron to thallium and pushes the thallium to the next group, which is under the carbon. So this alloy has some features like a carbon. So there is a lot of work that is being currently carried out in these Zintel phases. Similarly, calcium, CaZn2, that's again is Zintel phase. Zinc is on the right-hand side of the periodic table, calcium is on the left. So when you make an alloy between them, you get a Zintels. These Zintels have unusual magnetic properties. More importantly, they have thermoelectric properties. So those of you who are interested in this, they can follow the literature by Susan Koslerich from UC Davis. Zheng Zhao from Rutgers University has been working on this. And Mercury Kanetsidis from University of Michigan has been working on this. But these are the compounds, extremely important. Thermoelectric materials, I'm sure most of you know this already, is when you apply electrical potential, they create hot or cold zones. So you can make what we call compressor-less refrigeration systems using thermoelectric materials. Similarly, thermoelectric materials also can be used to recover wasted heat and convert that into electricity. So these are all the applications of this. There's a very active research currently going on both in China, Russia, Japan, and US, UK, everywhere, because people want to find a good material, thermoelectric materials, for energy harvestation. Good. So
Is that used in solar panels, maybe?
not solar panels. These are solar panels is light to electricity. This one is from heat to electricity.
Got it.
Okay. So for example, the very first thing was, if I take two metals, like let's say antimony and bismuth, right? These are called dissimilar metals. So when you make a joint here and put a drop of water here and send electricity, depending on the direction of the electrical flow, this water will freeze to ice or vaporize to vapor just by changing the potential here. So that was the first thermoelectric effect that was discovered. Anytime you combine two dissimilar metals, the junction itself is thermoelectric junction here. This is how they create refrigerators using DC electricity. Now, if those of you have gone in a limousine, you have a nice refrigerator in the car. That refrigerator does not use AC electricity, but this is made from the thermoelectric principles. So apply the potential batteries. You can use a battery and you can keep your food cold because you can create several cold junctions. Does that make sense? And folks, the next thing that we're going to talk about is close packing. Remember, we talked about face-centered tubes. If you have a face-centered tube, you have atoms at the corners and the centers of the faces. Now, this is a face-centered tube with an effective number of 4 atoms per unit cell. So I think we talked about this before. I can show you a picture of this. This is a face-centered tube here. Right? Now, in this face-centered tube, if you really pay attention very, very closely, if you use any 3 of the face center and 1 corner, 3 atoms of the face center and 1 corner, that looks like a tetrahedra. And if you look at the place here within the tetrahedra, that is an empty space, which is called a tetrahedral hole or T-hole. We talked about this briefly. So using this model, how many tetrahedral holes will be there in the face-centered cube, inside the cube? So this is the tetrahedra that I'm talking about. 1, 2, 3. 3 face-centered atoms. This is the corner atom and 3 face centers. If you combine them, that looks like exactly like a tetrahedra. That's a hole right there. That is your tetrahedral hole. So how many such holes will be there within this structure?
Would there be 8?
You are absolutely correct, Devon. There will be absolutely 8 of them. So if you are math savvy, you can say this coordinate is 1, 8, 1, 8, 1, 8. If you were to look at that point there within the cube, there will be 8 such points. So if we choose 8 corners, each corner has an origin here, you can locate the point 1, 8, 1, 8, 1, 8, using that as an origin. That will be a tetrahedral hole. Similarly, you can go to the next atom in the corner, consider that as the origin. Again, draw the 1, 8, 1, 8, 1, 8. So you will have a total of 8 tetrahedral holes. So what is the relationship between Z and the number of tetrahedral holes? If I have n number of atoms, how many tetrahedral holes we will have then? If you have 4, you get 8, right? If you have n number of atoms, you will get 2n number of tetrahedral holes. The reason I'm bringing this up is, in some crystal structures, you can use the tetrahedral space to add another atom or another species, another ion, and derive different crystallographic structures. Okay, so it's very important to recognize 8 tetrahedral holes in this. Similarly, if you now look at the body-centered position of the face-centered cube, that is in the middle, what should be the coordination of that? How many atoms it is close to? So if I look at this one here, this is the face-centered cube. Now I'm looking at the middle of the cube, that is the center right there. Clearly, as you can see, using that center, you have 6 atoms close to it in an octahedral position. So that position here is called an octahedral hole. All right, so how many octahedral holes will be there in a face-centered cube? Any thoughts? Yeah, the body center position is there. That is an octahedral hole. I want you to look at this atom or a position on the center of the edge here. So if you look at the face-centered cube structure, and if you look at the center of the edge here, you can see this center looks like half octahedra, and the next cube will have the other half of the octahedra. So that center is also an octahedral hole. So I will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sites. So if I have a hole on the center of the edge, what should be its contribution to the cube then? Is it 1/2, 1/8, 1/4, 1/2? What is it? 1/3? Any thoughts on this? We know if it stays in the corner, it contributes 1/8. If it stays on the face, it contributes 1/2. If it stays on the edge, what would be its contribution?
One-fourth.
John, you're absolutely correct. That's 1/4. So how many edges we have in a cube? Every cube has 12 edges, right? You agree with me? So if each one contributes 1/4, 12 times 1/4 is 3. So effectively, there are 3 octahedral holes here and 1 in the middle. So 3 plus 1 is 4. So a face-centered cube will have an effective number of 4 octahedral holes and 8 tetrahedral holes. So in other words, the number of octahedral holes is exactly n. If I have n number of atoms, I will have n number of octahedral holes and 2n number of tetrahedral holes. Okay, so now I can put atoms or ions into these positions and be able to calculate the crystal structures. So let me show you a few examples of how one can use octahedral and tetrahedral holes to understand the crystal structures of inorganic solids. But before I do that, are there any questions so far? Are we okay? So let me give you some examples of this. Let's start with the rock salt structure. We all know about rock salt. That's the sodium chloride. So how do we understand the crystal structure of sodium chloride? There are many, many ways of imagining the structures, but one elegant way of looking at crystal structures is looking at their arrangement and try to understand the relationship between the structure and the tetrahedral or octahedral holes. In the case of sodium chloride, we have a face-centered cube of sodium atoms. So these are all the sodium atoms here, sodium ions. On the centers of the faces and the corners. Got it? That is a face-centered cube of sodium ions. Now, if I were to put the chloride at all the octahedral holes are in the middle here and centers of all the edges. Right? Remember we talked about this just a minute ago. That structure, surprisingly, the crystal structure of the rock salt, which is sodium chloride structure. Okay, so if you want to see a physical picture of how that looks like, I can bring the structure from here and show you in a three-dimensional space. That's the structure that I'm talking about here. Can you all see this? So if I can bring this closer, you can see you can call sodium ions red and the chlorides negative. Either one, they are interchangeable. And that is the resulting structure. So if you now look at this to red, if you look at that, that is the unit cell length here. At the center of the edge, which is the octahedral hole, you have the chloride ion. So sodium and chlorine alternatively, they're arranged to give you a three-dimensional lattice. So this is the most important structure of crystallography. This is sodium chloride structure. Although it is used for sodium chloride, there are many, many compounds that do crystallize with this, like for example, calcium oxide, magnesium oxide. The only difference is you can now imagine magnesium ions occupying the sodium sites and oxygen replacing the chloride. And the resulting structure is the calcium oxide structure. All right, similarly, potassium chloride is the same structure. There are certain complex compounds that may look very complex, but still they adopt the sodium chloride structure. For example, if you look at zirconium pyrophosphate, Zr P2O7. Quite interestingly, zirconium pyrophosphate also adopts sodium chloride structure. So where there is sodium, the zirconium replaces the sodium here, and in the P2O7, you can write it as if it is a POP. It's a diphosphate ring with an oxygen bridge here. Now, if you put that oxygen, bridging oxygen onto the chloride side, the resulting structure is the structure of the zirconium pyrophosphate. This is a material which is quite unusual. It contracts when you heat and expands when you cool. It's just opposite to what we see in normal materials. This is what we call negative thermal expansion material. So when you heat it, it contracts. When you cool it, it expands. That's not how the metals behave. That's not what the common sense is, but this is a very special compound. And the property of that is attributed to the crystal structure because there's a lot of openness here that kind of collapses when you heat. Am I making sense here? So we'll take another example of crystal structures using tetrahedral and octahedral holes. We'll talk about, let's say, calcium fluoride. Calcium fluoride is a very important crystal structure again. This is also called fluoride. Whenever you are dealing with precious stones, calcium fluoride is one of those compounds that is associated with the precious stones. So what the jewelers do is to remove the calcium fluoride, they heat it up using a torch. So this flows in the jeweler's torch, and that's the reason why it's called fluoride, because it flows out of the torch. Now, if you look at the crystal structure again, very simply speaking, you can imagine all the calcium atoms at the face centers. In other words, the calcium ions form a face-centered cubic lattice. And the fluorines occupy all the tetrahedral holes. We said we have 8 tetrahedral holes. So if you fill in fluorides in all the tetrahedral holes, the resulting structure is called the fluoride structure. Am I clear here, folks? Even if you look at the stoichiometry, right? Effectively, there are 4 calciums because it's a face-centered cube. Effective number of calciums is 4. And there are 8 fluorines. So if you look at the ratio of calcium to fluorine 1:2, that is what this is, CaF2. Am I making sense here? Are you okay? Similarly, you can also have what we call anti-fluoride structure, where you reverse the anions and cations. In fluoride, in calcium fluoride, the anion stays in the tetrahedral hole and the cation forms the face-centered cube. If you reverse the roles, such as K2O, potassium oxide, is the same structure, except the potassium occupies the tetrahedral holes and oxygen forms the face-centered cube. So that is the crystal structure of antifluorides. So this is the difference between fluoride and antifluoride. Similarly, the compound zirconium dioxide adopts the same crystal structure, just like calcium fluoride. So the zirconium goes and sits on the calcium sides, and the oxygen sits in the tetrahedral holes. This compound is very important because this is used as an electrolyte for solid oxide fuel cells. Essentially, if you have a high temperature fuel cell, you can use zirconium oxide electrolyte. This zirconium dioxide, when you heat it to very high temperatures, it forms a vacancy, and that vacancy provides a path for the oxygens to move down the lattice. So it's an oxide ion conducting electrolyte, which is what we need for the design of a fuel cell. And commercially, they're available. In Australia, for example, several of the supermarkets and the hospitals are run by the fuel cells. They're extremely friendly. You can just use hydrogen and oxygen, and you can generate very good electricity and heat. So this is a very important area of research that is being carried out. Questions up to this point? All right, so let's move on. Another different type of crystal structures. Another very important class of compounds are called rutiles. Rutile is the name of a mineral whose composition is TiO2. TiO2 also has several polymorphs. Rutile is one of the polymorphs. Anatase is another polymorph that is used in the photochemical cells, especially in the solar cell constructions. And then we have also bronze-like structures and different type of crystallographic variations of TiO2. But the most important one is TiO2 is rutile. So how does the structure look like? Rutile can be derived from a tetragonal unit cell. Remember the tetragonal unit cell, right? Tetragonal is A equals to B, but not equal to C. All the internal angles are 90 degrees. Now, if I were to put titanium atoms at all the corners and the body center, okay, that is the arrangement of titanium. So how many effective number of titanium atoms we are talking about here now? What's the effective number for the body center cubes? I cannot read chart here because my screen is small. Yes, Michael?
Oh, yeah, I said 2.
2 correct, yes. We should know, we already know this, right? There are 2 of the titanium, so we'll have 2 titaniums. And then now, watch this. You have an octahedra of oxygen atoms. So that's a TiO2, TiO6 octahedra with 2 oxygens on the face, opposite faces, 2 oxygens inside. So how many effective number of oxygen atoms you're talking about here? These 2 contribute 2 atoms. Although we have 2, because on the face, they'll contribute only 1 half, right? So 1 oxygen there, 1 oxygen there. So a total of 4 oxygens, right? So that is the resulting structure, TiO2. That is the rutile structure. We have dirutiles, trirutiles, a lot of work goes on in this area because they're also used in the construction of lithium-ion battery, anodes, and cathode materials. So it's a very important class of crystal structures. Any questions up to this point? I understand that nobody wants to talk because this is an online class. It is sad, but it's okay. We will continue on this. I'm not going to complain. I hope you are all learning. That's all I'm thinking. We'll move on to another important class of materials called perovskites. Perovskite, again, is the name of a mineral whose composition is CaTiO3, calcium titanium dioxide. Okay. So this is calcium titanate, CaTiO3. So if you look at the crystal structure of this, there are, of course, thousands of compounds that are very similar to perovskite-like structures. So here what happens is you have titanium in the center and oxygens on the centers of the faces, and the calcium atoms occupy the corners. Okay, so that is a very important crystal structure. So here you have TiO6 octahedra. If you go to the next one, again, TiO6 octahedra, these are all corner shade, 3-dimensional network of TiO6 octahedra. And that arrangement makes these compounds very interesting because you have all kinds of properties like capacitors, superconductors, semiconductors, and the recent solar cells are made from perovskite-based solar cells. There are basically, methylamine lead iodides. So you can have a methylamine cation here, lead here. Instead of oxygen, we can have an iodine there. Those are basically called the the perovskite-based solar cells. So there is a lot of interest in these compounds. This is one way of writing it. You can also write the same structure in a different way. Like, for example, you can write the titaniums at the corner. And oxygens on the centers of the edges, and calcium in the middle. That's also the same structure. It's just a different representation. If you take the previous structure, move all the atoms by 1/2, 1/2, 1/2 in 3 dimensions, we'll end up with this. They're identical structures. Some people like to look at perovskite in this way. Some people like in the way I have described in the previous one. Both are identical. All right, so this is how we can look at this. Again, if you look at the stoichiometry, even in this, I have 1 calcium. There are 8 titaniums, but because they are in the corner, there is only 1 titanium effectively. And I have 12 oxygens, but then they are in the edges. So 12 times 1/4 is 3 oxygens. So again, the stoichiometry is CaTiO3. Right, so that's how we can look at the unit cell and find out what the formula of that compound is. All right. So in some cases, we also have other structures that's called diamond structure. Diamond is very well known to us. So we can also understand the diamond structure very simply based on what we have been talking about. So you can imagine a face-centered cube of carbon atoms, carbon, 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 everywhere on the centers of each face and on the corners. And then, remember, this should have 8 tetrahedral holes. So if we use 1/2 of those tetrahedral holes, so if you put another carbon here, carbon there, carbon here, carbon there, only 1/2 of tetrahedral holes, the resulting structure is that of what we call the diamond. So face-centered cube, only 1/2 of the tetrahedral holes are filled in this one. Am I making sense here? So we're not introducing new concepts. We're looking at the same structure and then looking at different ways of examining this. Let's look at a diamond-like structure, which is zinc blende structure, zinc sulfide. Zinc sulfide has a diamond-like structure where you have the zinc atoms from the face-centered cube atoms at the corners, at centers of the faces. And then again, if you use 1/2 of the tetrahedral holes and put sulfur there, only 4 sulfurs instead, although there are 8 parts, we only occupy them partially, only 50% occupancy. The resulting structure is what we call zinc sulfide, which is again a very important crystal structure. Let me see if I can show you a picture of that in reality. So I assembled a model. You can see here, you have the blue and the gray atoms here, right? So the blue atoms are the zinc atoms and the gray ones are your sulfurs. So 1/2 of the tetrahedral holes are occupied. If you look at the gray sphere and look at the next nearest neighbors, you have only 4 of them. That's a tetrahedra. So there is an interconnected tetrahedral networks that give you the zinc sulfide. So if you replace all the zinc and sulfur by carbon, the exact structure is that of the diamond. So they're very similar. In the case of diamond, all atoms are same. In the case of zinc sulfide, we have sulfur in the T holes and zinc in the face-centered cubic structure. That makes sense, folks? Any questions so far? Okay, so in the last 10 minutes or so, we'll talk a little bit about the lattice energies. How strong are the solids? How do we know? So these are calculated by what we call lattice energies. Especially, I think I have uploaded a couple of videos in the Born-Haber cycle, so you can also look at this. But I'll give you a brief introduction about what lattice energy is. Lattice energy is a very tricky definition. It is the energy released when oppositely charged ions of a solid are brought together from an infinite distance and make 1 mole of a solid. The total amount of energy released is what is called lattice energy. So you got to take 1 mole of sodium ions to one corner of the universe, 1 mole of chlorides to the other corner of the universe, and start bringing them together and then see how the energy changes. The total energy released when 1 mole of sodium chloride is formed is what is called lattice energy. As I told you, this is nearly impossible to do it experimentally. So lattice energies are either calculated qualitatively or through indirect means. So I will show you that very quickly. So in general, the lattice energy, which is basically related to the force of attraction between a positive and negative, is proportional to the charges of the ions divided by the square of the distance they are separated by. That distance they are separated by depends on the sizes. The larger the ions, the larger the R, so weaker is the attraction. So more importantly, the charges. If the charges are large, no matter what the size is, the lattice energy is going to be large. So let me give you an example here. Let's say if I have sodium chloride and calcium oxide, which one should have higher lattice energy? Sodium has +1 and -1, calcium is +2 and -2. So in the case of calcium, 2 times 2 is 4. In the case of sodium, it's only 1. So calcium oxide is supposed to be extremely strong. So lattice energy is very strong, which also tells you the melting point of calcium oxide must be high because the force of attraction is large in the case of calcium oxide compared to sodium chloride. So that's one thing. Suppose if I have same charges like calcium oxide and calcium sulfide, which one should have higher lattice energy? Because charges are same. If the charges are same, only then you go to the sizes. If the charges are different, then you go by the charge alone. You don't have to worry about size. You worry about size only if the charges are equal. So in the case of calcium sulfide and calcium oxide, charges are same, but sulfur is big compared to oxygen. What that means is the R value for calcium sulfide is high, which makes the force of attraction weaker. So calcium sulfide will have smaller lattice energy. In other words, the ionic strength is not as strong as it is in the calcium oxide. So sometimes in the exams we'll give you a bunch of compounds and ask you to arrange them in the increasing order of lattice energy or ionic strengths. So you should use this guiding principle. But if you want to really calculate numerically, because lattice energy definition is very tricky, we go by what we call Born-Haber cycle. So I have some data that I'm going to show you and show you how to calculate that one. Let me see what that. We should have some examples of what's like this. Right here. Let's say if I have potassium chloride. How do we write the lattice energy equation for this? That's going to be potassium ions in gas phase, plus chloride ions in gas phase, forming KCl. The delta H for this is going to be the lattice energy. It is the amount of energy formed when 1 mole of a solid is formed from stoichiometric amounts of the anions and cations brought together from an infinite distance. That's your lattice energy.
Could you move the camera up because I can't see which.
You can't see it? Okay, I'm sorry. Can you see that, please?
Thank you.
Okay, good. Yeah, you got to let me know. All right, so we'll talk about potassium chloride. Although we can't estimate this experimentally, we can do this indirectly. So let's look at potassium chloride formation. So when you make potassium chloride, what you do is you take potassium solid plus half a mole of chlorine to make KCl solid, right? This can be experimentally measured in a bomb calorimeter. So this is what we call the heat of formation. This can be experimentally determined. But then to get this, if you now look at the anatomy of this process, how KCl is formed from potassium solid and chlorine gas, we need to go through several steps. The first thing is potassium solid goes to potassium gas. That is your delta H of heat of sublimation. That value is about plus 89 kilojoules. Heat of sublimation is always endothermic, right? That's plus 89. And then we got to break down the CO2 gas into CO. This is a bond breaking. So this is the bond energy of this, of dissociation. This is 1 mole is 244. So it's only 1/2 of moles. So it's going to be 122 kilojoules. And the potassium gas must be made into potassium ions in gas phase. That's your ionization energy. That ionization energy is plus 425 kilojoules. And finally, we have chlorine atoms in gas phase accepting an electron to make chloride ions. That's an electron gain enthalpy. That is EGE, which is negative 355 kilojoules. And finally, we have potassium ions in gas phase and Cl minus in the gas phase making potassium chloride solid. That is your lattice energy. This is the unknown here. The beauty of it is, if you add all these equations, you get potassium gas cancels out, Cl gas cancels out, the electron here cancels out, and then we have Cl minus cancels out, the potassium ion cancels out. What you get basically then is this. Our Hess's law tells us that if I know the heat of formation of potassium chloride, which is basically negative 438 kilojoules, this is known experimentally. This negative 438 must be the sum of all these delta H values. And in here you have the unknown lattice energy. So you can solve for this. So when you solve for this, the lattice enthalpy or lattice energy comes to negative 719 kilojoules. Okay, so that is how we can calculate the lattice energies. This is clear too. This is the essence of Born-Haber cycle. So I think it's already 3:15. I have a couple of more topics to cover, which we can do next Tuesday, because I don't want to rush this one, just very small topics. One is called Kapuscinski's equation. The other one is Madelung constant. These are the two things I'll briefly talk that will not take more than 5-10 minutes. And then we'll continue with the coordination complexes next week. So is everything okay so far, folks? Anything not clear?
Yeah, I think I'm going to review this lecture and then ask question next lecture.
Sure, yeah, I mean, this is a lot of material that we covered today. But it's good that we covered this and all the videos that I've uploaded. Between all that, you should see a good idea about solid state chemistry. All right, if there are no other questions, we will see you next Tuesday. But make sure next Thursday's class meeting, you all go through those intro to coordination complexes, because I will not have time to teach you how to name the complexes, because I'll be saying the names very quickly and writing down the formulas. I don't want you to get lost. So please, next Thursday class time, go over the videos that I uploaded yesterday. See you then, folks.
Bye, Chari.
Bye-bye.
Thanks, Char.